Today, I want to jump into talking about how to use deep learning with just deep learning in general, and how Watson Studio can be used to do time series prediction. So my name's Jeremy. I'm a data scientist and developer advocate at IBM Center for Open Source Data and AI Technologies. My background is, so I've been with IBM since about 2015. I started working at the Spark Technology Center, which was an open source framework for big data and machine learning, mostly not really deep learning. And we basically worked on all aspects of Spark, including client advocacy, developer advocacy, public outreach, and then also training people internally on how to use Apache Spark. And then basically we expanded that mission to cover most of the AI technologies out there, including graph databases, Kubernetes, but mostly the deep learning frameworks. So now we're really into TensorFlow, PyTorch, Caffe, and the like. Our primary interest is TensorFlow. But my background is not computer science. I got a bachelor's in chemical engineering from Cal across the pond, and got a PhD from UCSF in computational biophysics, where I did mostly protein folding type calculations, drug design calculations, high performance algorithms for computing, those kinds of things. And so I got, protein folding definitely has a big time series aspect to it. There's lots of, trying to determine stationarity of time distributions, and detecting convergence, and master equation models, and all of that kind of stuff. So I thought it would be kind of, when I heard that neural nets could be used for time series models, I thought, oh gosh, that might be kind of a fun thing to try to get working. So, but then after that, I did some postdocs at UC Berkeley, Lawrence Berkeley, went out to Livermore for a while, where I did more bioinformatics type applications, which kind of got me into the Insight data engineering program, where I joined the private, developed sort of private sector technologies and big data technology, or my skill set around that. So that's my background. In general, IBM's background with open source has been, a real history of leadership. We were the founding members of the Apache Software Foundation, founding members of the Linux Software Foundation. Virtually every major open source project will have IBM featured prominently as contributors. So we definitely are proud of that heritage, probably more proud of it than most large tech firms. And so we've been doing open source for quite some time, and our particular group is completely dedicated to open source. So when we say open source data and AI technologies, we're talking about all the open source frameworks primarily. And then we're also talking about, the open source, when we say open source data, we're talking about data that, that is open and freely available, has good governance, and also formats, file formats, such as the Onyx format, which we'll be talking about maybe in the next month or so in future talks. But our goal here is just to make AI solutions easier to create, deploy, and manage in the enterprise. And as I mentioned, this is kind of a retooling of the Spark Technology Center. For those of you who may be familiar with the STC, it was quite well known for its contributions in the open source community. But the things that we're going to talk about today, we've got this whole framework. We're going to talk about the model asset exchange, fabric for deep learning, and then the more exploratory process of analyzing data. So I just want to blow this up a little bit, and then you can see. So we've got lots of frameworks here that we're concerned about, but really, the Watson Studio environment really is built on top of Jupyter. And I'm guessing, just a quick show of hands, who uses Jupyter maybe daily? Or yeah, okay. So basically, the Watson Studio is just a Jupyter front end that connects to various remote kernels, cloud-hosted kernels, various environments. So you can connect to a Spark environment, you can connect to a GPU-accelerated environment, you can connect to a S3, you can connect to all kinds of remote clusters, but it still has that Jupyter environment that you're working in. So it's quite nice and quite natural, even though you're working in significantly different hardware space. The front end is very familiar to you. So so these are the areas that we're going to be working on. There are two main projects that Coday is concerned with, and one is the model asset exchange. And I'd really encourage you to check this out, because even when we started this, we didn't realize how far along the model zoos were that are out there. How many freely available, perfectly open neural network models that are just ready to go are out there that you can run. So basically what we did is we went and we vetted a whole series of model zoos provided by all the open source frameworks. We made sure that the data had good provenance, that you could use it in commercial applications. You didn't have to just use it for research applications. You didn't have to do any special permissions around the data that was used to train the model. Made sure the code that was properly vetted and had the right licensing and all of that. So you can just grab these things and run with them. But it also is just a great tour of what these neural networks are capable of. And of course, we've seen some image detection models and some other things. You can't quite see some of these, but we've got a facial age estimator, weather forecaster, which is actually a version of what we're talking about. But the important thing to remember is that these are all pre-trained models, so you don't have to deal with the training aspect of it. You just feed so for example, we have something called object detector. It has, I don't know, on the order of hundreds of objects that it's trained on, so you don't need to do any training to get those to work. So that's what's nice about it. We tried to fix some models that had some transferability already. Facial age estimator, for example, as long as you're not trying to estimate the age of, let's say, cats or something, this is going to work pretty robustly for a lot of examples, so you don't need to do any retraining. And you can get a very quick sense of how these models perform, the kinds of tasks that they can carry out. For example, we've got image caption generator and some other ones that are quite nice. You can deploy them on our API framework and then just make REST calls, or you can go to the GitHub and download the source code and compile the Docker image, and then just run the Docker container from wherever you like. And so it's all completely free and completely open until you start using the web service or something like that. I can't remember, but. So those are for the pre-trained models, is the model asset exchange. And then these are all the stats. There are also some patterns that are related to it. Now, for trainable models, you have to have a slightly more complex framework because it's still the same idea where you're going to want to deploy this. Now it's actually slightly leaning more towards deploying on remote hardware. That way you can spin up a GPU instance somewhere remotely. So this has a little bit more machinery around keeping track of your asynchronous job requests and job monitoring and all that kind of stuff. But the same idea is there. These you can deploy this using Kubernetes, and then you have a remote container sitting on one of our hosted GPU instances, and then you can just spin it up for the training and then spin it back down. So, and this is getting to the point now where it will be supporting slightly more sophisticated environments like Horovod, which has allows for parallel training using MPI, and some other, and I think some other frameworks. We're going to be just getting into this Onyx format that we're going to be learning a little bit more about in the near future. So I'm looking forward to finding out about that. But so those are the two frameworks. But the two frameworks that are really useful when you either know what what the task is, and you feel like you've got a network that's trained, or you know that you need to train a network, but you're not really experimenting with the architecture of the network or anything like that. So you just know that you've got a network and you just need to retrain it on, for example, facial age estimator, just retrain it on cats if you want to estimate cat ages. But there's still a large grouping of problems that don't fall into that. You don't know what the best architecture is. You don't even really know what the data set might be, which we spend a fair amount of time talking about explainability and which features are relevant for describing creditworthiness, for example. And it takes a little time noodling that out before you can just spin up a an API and start running sort of these production level containers to train your code. So really, if you look at this, this workflow, you've got execution and consumption, which is really the max and the fiddle, and then providing APIs or some engineering solution that you have in-house. And those are probably well-worn paths within your company or something that's well understood. But there's this huge section of discovery where you got to find the model, you got to get the code, you got to test it, you got to verify it, you've got to do all that stuff. So you're really back to working in your notebook environment, or you're doing some exploratory modeling. And what happens when you do this? If you want to do this with a neural network, you're gonna even with MNIST, you're waiting a while to get this thing trained, right? Even with the smallest interesting neural network that you can come up with, you're really pushing the resources of your laptop or your desktop or whatever it is, and maybe you don't want to go out and buy a GPU node right away. So this is the kind of thing that we encourage you to try to spin up a GPU accelerated studio instance, for example, and then you've got immediate access to a GPU node. Same thing with the Spark cluster. You can have immediate access to a Spark cluster rather than waiting until you outgrow your single node machine. So it's a good place, good sandbox for that kind of thing. And so this is what the environment looks like. It basically looks like a Jupyter notebook. It's just got some additional collaborative features and things like that. So this is a typical interface, and it does the same kind of inputs and outputs that you would expect if it does the pandas-like output of the data frame. And this also just to show you, rather than do a live demo, I just wanted to throw up a couple screenshots so you can see what the notebook looks like rather than scroll through the notebook. I did also want to point out that there are there's a little bit of boilerplate code that allows you to connect to a remote cloud storage instance, and that's about the only complexity that's added, really. That's the only time you see anything under the covers when you're running on these Jupyter notebooks. So let's just take a step back and kind of remind ourselves what a neural network is, and we can talk about, now we can just kind of, okay, this is the neural network that we're going to be using for time series modeling. This is one recommended architecture. So I'm just going to walk through how this is going to look. And in order to do that, we kind of got to jump back a little bit and understand what a neuron is. And so a neuron really is these. You've got these features that come in. You add them up with a set of linear weights. You get this x times w. This is a vector operation here plus a bias term, and that gives you the z term. And that's just this superposition of all these inputs, right? This is just the multiplication addition operation. And then that goes into something called an activation function. This would be the neuron. And this lights up in various ways. Probably the best way to think about it is this logistic or hyperbolic tangent, where it's basically a switch. It hits some threshold and it lights up, right? It's either on or it's off. That's the historical way that we've thought about neurons in the context of neural networks. Numerically speaking, most of these terms are use the ReLU, the rectified linear unit, just because it has better numerical properties. So all the ones that we're using here have the rectified linear unit. So and we can put all these together to form a dense layer. So we've got layer 1 here. And these, basically you can think, you can, don't worry about the neurons here. Just think about the arrows coming out. Those arrows are numbers. Those numbers are getting piped into another layer, and that other layer is being, all the numbers are being added up using that addition multiplication operation, and then an activation function transforms that into some switching value. But the important thing to remember is that these neural networks are always assembled in these layers. And the layers really only connect to the next layer or the previous layer. So when we say a densely connected layer, this is always really going to be the way it's done. It's just this sort of, and you probably, the best way to think about this is just as some orderly arrangement of parameters to form some complex nonlinear function that you're going to fit data to, really. And then at the end of the day, you've just got a function that you've got a function and you've got values, and you want to just fit the function to that. So this is the classic MNIST model. As we said, we've seen almost endless examples of image processing. This is really a very mature field at this point in the neural network field. So, but this is about as simple as a useful network as we can possibly construct. But it's useful to review it, or maybe to see it for the first time, so you can understand how the philosophy behind these things. So you've got basically you've got an input and you've got an output. So the input is this image. This image is just this list of pixels. The pixels is unwrapped, so there's actually 28 by 28 pixels. That's unwrapped into a feature vector of 784 values. Each one has a value that's fed into the first layer, which is the input layer. And the number of input layers matches the number of values, and those get piped in. And then we have a whole series of fully connected networks. And you can be clever about whether they get bigger or smaller, or how deep they are, and all that kind of clever stuff to get the best architecture. And there's also lots of complexities that we really don't need to go into here about creating convolution layers and things like that that are more particular to image processing. So there's a lot of really clever image processing tricks that go into these image networks that we won't really need to cover here. But this is the basic idea. So you pipe in this vector output. This has 10 neurons. If you make the top one as 1, the last one is 0, then if the 7th neuron has the highest value or lights up the most, then we would identify the output as recommending that the image corresponds to number 7. So it's a classifier, basically, returns a classification output. So really, I mean, and even the optimizations for classifiers are slightly different than something that produces a floating point number. So the fact that we're dealing with floating point number in time series is actually kind of a unique aspect to the neural network. Most of the tasks in neural networks are classification tasks, not floating point predictions. So the sort of the next wrinkle to this is the recurrent neural network. And this usually represented this way, which is super confusing. Anytime I see recursion, I always get confused because I wrote my thesis in Fortran. I always unroll loops. So recursion, I think, is a unnecessary unnecessary abbreviation of notation. But here we have here we can actually unroll these loops here. You can actually recurse this as often as you like. In practice, you do unroll these loops a finite number of times the way they're constructed. So the idea here, though, is that you have an input, and this neuron gets modified. It has the neuron now has an internal state that gets modified every time you feed it an input. And then what you do is you feed it the next input being the same feature but a different step in time, right? So now it explicitly understands that the next thing that's happening is connected to the previous state. So it has to maintain a memory state in order to process that information. So then we pipe this X in, modifies the state, and now the neuron is in a new state. The new state is, and then it produces an output. The new neuron, this is the same, it's the same neuron, but a new state is fed a new value, it modifies the state, and then also produces a new output. So it connects previous events. It has a memory of previous events. So the place where this really shines has historically been language processing, because phrases, words are strung together in a meaningful way, and each word that follows the next word is connected to the previous word in some way. And so this is again, with time series is almost kind of a sideshow compared to the work that's been done in language processing. So this is the famous LSTM neuron. There are a few. There's one called the gated recurrent unit, which is slightly more It has fewer parameters and is thought to have better performance characteristics. For whatever reason, you see this one much more frequently. I just think it's better understood. It has lots and lots of internal parameters. The idea being, again, that it has basically the capacity to remember the important things, forget the unimportant things, and depending on the interval of training, it has capacity to keep the notion of the previous time step having a stronger influence on the state than maybe 5 states back and things like that. All of that is thought to be contained in this pretty complex neuron, but at the end of the day, this is a neuron that produces an output and returns a state, right? And so this is how it's connected now. It's just got 2 parameters that sort of correspond to its state, and they're sort of piped through the LSTM unit in various ways. So now you can feed your time series in and then have it return a time series. You can have a time series of a different length go in and have a different time series. The time series going in can be of different length than the time series going out. You can call it multiple times and have it return multiple states and in an arbitrary way. So you're not constrained in that way depending on the architecture that you use. So this is the Encoder Decoder multivariate time series. This is modified from a blog and a text that's been written. Very, very nice blog series and book. And we're just sort of modifying it slightly. And here we just have this whole set of inputs. We're missing all these fully connected arrows just because it makes the slides so busy. But at the end of the day, you have an input and an output. You've got a feature vector now with 8 values and 14 time steps. So that means that these input values here, there's going to be 8 input x's, and each one of those x's is going to have 14 time steps associated with it, 2 weeks worth of data in this case. That's gonna feed into something called an LSTM encoder. And what's happening here, these are the LSTM neurons right here, this column here. And then you have something called the repeat vector, which just hits that LSTM an arbitrary number of times, in this case 7 days, and that's going to produce a time series now, not of 14 days, but of 7 days in length. So if you just look at this first network here, this in principle could just be its own generative network, right? You could, you give it 14 days worth of data, it makes a prediction for 7 days. But what happens is that this is actually thought of more as an internal representation of the data. So there's something called, how many people are familiar with an autoencoder? Okay, so this is sort of the idea behind an autoencoder. What you do is you have a neural network with inputs, and then you reproduce those inputs with the output, and then you let the neural network kind of morph the data into some clever representation of the data somewhere in the middle. And it's thought that representation somewhere in the middle is a meaningful way of encoding the data. And so that's what's happening here. We're pushing it through this neural network. There's an output at the end that we have to fit the data to, but you're giving it some wiggle room and allowing the entropy of these parameters to produce some really interesting representation of the data that can then be more effectively decoded and then rigidified and pumped into the fitting process. So that's what's happening here. We're just doing an encoding process. So we've created this encoded time series now. Now we're going to pipe that through another LSTM, and that's just going to be the decoding process. So this is all the time series stuff is happening right at the beginning. And then the output of that gets piped into this time-distributed dense layer, which is really just a way of processing that data. So it's each time slice is now a dense neural network. So really this whole temporal aspect is not so much captured here. It's just sort of pumped right into these dense neural networks. And this is kind of a little bit more like a kind of a static, like instead of saying that this is a time series, it's just saying these are 7 pieces of data. Let's push through that and try to make a prediction with that. And then it goes to this 100 by 7 100 by 7 neurons, and then that eventually goes to this last dense time-distributed output layer, which is 2 by 7 neurons, which means we're predicting two variables with 8 inputs. So we've got multivariate inputs and multivariate outputs. So that's the idea. That's the architecture that we think will turn out to be the most generalizable, sort of solve the majority of your problems. You just kind of adjust the size of the networks and things like that, and should be able to get good prediction properties. So, here's just an example of some of the cells that are in Watson Studio, or just a network here. And this is what it looks like in Keras. So you add an LSTM with 200 nodes. Okay, we remember that. We got the ReLU activation layer. Okay, we remember that. And then add the repeat vector with the number of outputs being set to 7. And then add the other LSTM layer, and then the time-distributed 100 node layer along with the time-distributed 2-node layer. And then use the atom optimizer, and yeah, you don't need to use cross entropy as the loss here, because we're actually going back to good old-fashioned floating point fitting rather than trying to do categorization. So and then we run this for about 50 epochs, and this is there's only 1,000 examples in this test set. But they're it's running at a decent clip, 6 millisecond per step. And I think this whole thing takes about a minute to run. So, and again, if you ever get a chance to use this model summary, this is a great way to do a sanity check. And again, you've got the layers. Notice the time-distributed layer is a 7 by 100, so it's got 100 nodes, but there's 7 by 100 of those nodes because it's a time-distributed layer. It produces all prediction for 7 series, and then the last one has got the 2 by 7. I think that the interesting thing here is we got 1,000 data points, but we have 500,000 parameters, and it's just this. There's lots of articles on this, but it seems like an unreasonable task to expect it to work well, right? But a lot of it is because of the entropy of the construction, the fact that it kind of self-regularizes the way it's built. So even you could do studies to see if it's overfit and things like that, but it is the way that the fact that any node can point to any other node introduces this degeneracy in the nodes that allows these neural networks to perform well, even when there's much more parameters than data in many cases. So. But you might want to take a look at that. You might want to evaluate. So we didn't really jump into the evaluation of the fitness of the model here. We're just saying, hey, we just hooked up the plumbing. We think this is a good network. Maybe why don't we try this one out? And so this is just an example of what the input data looks like. Mostly just to give you a sanity check. There's 14 data points for the input. This is energy data, so it's not a particularly interesting data set. But it could be substituted with any other data set, and certainly much larger ones. So, and so this is the actual data and the predicted data. So it does well on one. Looks like it needs a little bit of work on the other one, and that's basically it. That's how you might go about hooking this up. And so now, really, the easy part is hooking it up, of course, and then the hard part is doing the analytics and making sure you've got high quality data and good performance characteristics. So we didn't really get into that too much here. So with that, I guess I'll wrap up just a little bit earlier, and definitely really want to encourage you to try out the Max models on the Model Exchange site. Also check out our developer website. We've got lots of really great free resources on the developer.ibm.com. Lots of great patterns, lots of great examples, and lots of great blogs. So with that, I guess I can wrap up and answer any questions you might have.
Hi, could you go back a few slides where you kind of had the code and you listed the batch size and the epochs and stuff?
Yeah, this one.
Yeah.
Yeah.
Why did you choose a batch size of 16? mean, I don't see anything obvious. I'm just curious why your thought process on that.
Yeah, actually, I didn't choose that one. Okay, yeah, I didn't choose that. This didn't require a lot of tuning. I mean, the whole thing trained in under a minute. So we could fiddle with that and see what happens. Even the number of epochs, I didn't adjust. I just took 50 out of the box and ran with it, and seemed to get good performance. I really didn't evaluate performance on this in terms predictive performance. Mostly, it was just to making sure that we just wanted. Actually, the big question was, can we do this on a multivariate time series? Is it even possible? Because of the way the networks are constructed. Typically, it's a univariate output. They say the univariate output can be that univariate output could be a vector, but in fact, it really can be a extra node. So that was really the thing that we were more concerned with. But yeah, so yeah, I can fiddle with that. See what it affects. Yeah.